Question 7, we're given these two functions here, f of x and g of x, and we're told that the region R is bounded by these curves y equals f of x, y equals g of x, the lines y equals 0, x equals 0, and y equals 9. So we are going to be rotating that region R 360 degrees about the y-axis, and we need to find the volume of the solid formed. So first of all, because we're rotating this about the y-axis, we'll get these functions in terms of x. So this f of x here and this g of x. We're going to make x the subject for both of these. So we'll start with the f of x first. So we're given that y equals f of x. So we'll just write y equals, and f of x is x minus 1 all squared, and then just making x the subject, so we just square root both sides, and we just take the positive square root because we know that x is a positive number, and also for the g of x, x is greater than or equal to 0, so for both of these we just take positive square root. So square root of y is equal to x minus 1, and therefore x is equal to the square root of y plus 1. So now we'll do g of x. So if y equals g of x, then we have y is equal to x squared plus 1. So that means x squared is equal to y minus 1, and therefore x is equal to the square root of y minus 1. Okay, so before we carry on and find the volume of the solid forms, let's just visualize the problem so we can see what's going on. So I'll just get up a graph of this problem, and I'll show you what it looks like as we rotate it, that region R, about the y-axis. So we're looking straight down onto the xy plane here, and we can see our g of x, which is the curve closest to the y-axis, and f of x is this outer curve here. So we're going to rotate these two curves about the y-axis 360 degrees. So if we just turn our graph a little bit, then we can see the z-axis coming up here, and rotating these curves about the y-axis, it'll look like this. Okay, so there's our curves rotated about the y-axis, and as we can see, they form a three-dimensional shape. So this red shape here, that's our outer function, the f of x rotated about the y-axis, and we want to find the volume of that one first, and then we can find the volume of the smaller shape, which is that yellowy green one, and then we'll subtract the volume of the smaller shape from the larger shape, and then we'll be left with the volume of the solid. So you could imagine just filling in the space between those shapes with the clay, and that would be our solid formed. So we'll go back to our problem and continue to solve it. So our volume is going to equal the volume of our outer shape, which is pi times the integral, and our outer function f of x is going from y equals 0 to y equals 9. So that's our limits of integration. And then we have square root of y plus 1 all squared, and that is with respect to y. So just a quick reminder of where we are getting this integral from. I'll just bring up a picture of the solid forms when we rotate our outer function f of x about the y-axis. So we can imagine cutting our solid into lots and lots of thin slices. Then each slice is almost a cylinder, and its height is whatever our small change in y is, as we're rotating it about the y-axis, and the cylinder is going to have a radius of x, because that's our distance from the y-axis to our point on the curve, f of x. So the volume of the cylinder then would be pi times x squared times our small change in y, which we're calling dy, which is our height. So that's why we wanted to make x the subject earlier, because that is the radius of each of these little cylinders. Okay, so carrying on then, we're going to then subtract the volume of our smaller shape. So that was our inner function, so that's g of x, so that is going to be pi times the integral, and this one is going from y equals 1 to y equals 9, and it's going to be this here, all squared, so it's square root of y minus 1, all squared is just y minus 1, so we'll have y minus 1 dy. So now that we've got our equation, we're just going to bring up our graphing calculator and solve this on the calculator. So we're just going to plug this integral here into our calculator and solve. Okay, so working this out, we're going to get pi times our integral, and the limits are 0 up to 9. We have bracket the square root of y plus 1, and this is all squared, and that integral is taken with respect to y. So we get 268.606, so that was the volume of our larger shape, and then just subtract the volume of the smaller shape. So that one is going to be pi times our integral, and the limits this time are 1 to 9, and the integrand is just y minus 1, and we take that with respect to y, and that's our final answer there, 168.075. So we just need to round that to 3 significant figures, and then we get 168. So that is our answer for question 7.